Today's topic is about a binary heap. This is a combination of the binary tree and your project number 3. So before we start, let's take a look of the big picture. You've seen this picture before. It's saying that the whole space is about a graph theory tree, which indicating that we will have a rooted node to consider as the starting point. Inside of it, saying that no nodes can have more than 2 children is what we call a binary tree. In our previous topic, we look into the binary search tree, which means that all the nodes on the left side is smaller and all the nodes on the right side is larger than the node itself. Therefore, if we take a look at this picture carefully, you will see that the binary tree is a subset of the binary tree. However, it is not a binary search tree. So this is very important, and you need to understand the difference between the binary heap and the binary search tree. So after seeing the big picture, let's take a look of why do we want to study about the binary heap. This binary heap is mostly used for what we call a priority queue. So what is a priority queue? A priority queue indicating it's a space, a data structure that stores all kinds of different data. It will be able to let you insert whatever elements that you want to insert, and then the major task for the priority queue is finding the minimum quickly, and then we will be able to delete the minimum quickly as well. So all we care over here is the extreme case inside of all the data that we have. In this case, we say we want to find a minimum, use it, and then delete the minimum. And of course, the next item that we want to access is the second minimum of the priority queue that we have. Minimum can be changed into maximum. It does not matter whether you want to find a minimum or maximum. To do that, we actually have learned several different structures that we will be able to achieve that. The easiest way is we can have a storage, put whatever elements over there. When we want to find a minimum, we use a for loop to find a minimum. Until we find a minimum, we delete a minimum, and then we take the last element to substitute the space that we have been deleted. And we can keep doing that, of course. It's not a very structured way. Another one is the sorted array. For the sorted array, we can sort all the elements. Of course, they have been sorted already. However, if we want to delete the very first item, all the values need to do the shifting. And in saying that if we using a linked list implementation to do so, how about the insert operation? We will still need to insert into the location, spending some time to find the right spot to do the insert. The latest method that we have learned about the binary search tree can actually do the trick pretty well already, which means that we build up a binary search tree, a simple way of the building, and then if we're starting from the root search all the way to the left until we find a node that has no left child, that is the minimum. We can delete that, and that is going to be a pretty straightforward delete operation, and then we can continue doing so. So there are all of these things are available to do the task. However, the binary heap that we want to learn in this chapter gives the best performance to act as a priority queue. And therefore, let's take a look what it looks like. A binary heap supports the insert of new item and delete of the minimum item in a log worst case scenario. This is guaranteed, unlike binary search tree. For binary search tree, if we just use the straightforward way, if it is in a balanced shape, it is going to give us log n operation. However, there is no guarantee, because if unfortunately the items are being inserted in an extreme case scenario, just like the project number 3 that we have seen, you actually need to create a large space for holding those elements, or you need to use the end up with like a linked list way to search one by one. So this binary heap is actually gives you a guarantee that the worst case scenario is going to be log an operation, which is very fast actually. The best part of this is that it uses only a one-dimensional array to implement. It is the classic method to use to implement what we call the priority queue. So let's look into what is a binary heap. A binary heap, unlike binary search tree, it has two criteria, and both of them are very important. Both criteria need to be maintained throughout the whole process so that we can call it as a binary heap. The first criteria is it has to be a complete binary tree. And of course, we will talk about what is a complete binary tree in the following slide. The next criteria is that for every node X with the parent P, which means the parent is the one that we're looking at, the key in the parent is smaller or equal to the key in X. What does that mean? It basically says that the parent has to be smaller than both of their children if they have two children. That's the difference between priority queue, which is binary heap, versus the binary search tree. Because for binary search tree, left child is smaller, right child is larger. In binary heap, parent has to be smaller than its children. That's the difference. So let's take a look at the first criteria, complete binary tree. For a complete binary tree, it's a tree that completely filled, which means that if you have one node, it has to be the root. If you have two nodes, the next node would be the left child of the root. If you will have three nodes, then it has to be the root and both children. There is no other choices but filling up nodes one by one. So you can see that in this case, it is the binary heap with 6 elements. If we add one more item, it has to be in this spot. If we add one more item after that, it has to be in this spot, which is going to be the left child of the node 4. That is the idea of the complete binary tree. Of course, right now, you should feel very familiar with project number 3 because that concept is borrowed from binary heap. By doing so, the best thing that can happen is that we can use index to find their children. For the node of the parent, index location of 1, and of course we need to get rid of index of 0. To find your left child, you simply multiply 2 to your own index, then you can find the left child. If you use multiply 2 plus 1, you will be able to find your right child. And that is going to follow the whole binary heap criteria. Of course, because of the complete binary tree criteria, there is no null values in between the index of 1 until the last elements inside of the binary heap. And that gets rid of the troubles or the worst case scenarios that we were facing in project number 3, that this whole structure becomes the optimal solution for this type of question. The advantage of the complete binary tree is that the height of the complete binary tree is at most log n, because it will grow continuously. It will not have awkward shape. It will always maintain almost perfect situations of the binary tree. Left and right pointers are no longer needed, and this will actually gives you a very nice structure of the binary tree. To find your left child, you use 2 multiply your own index. To find the right child, use 2 multiply your own index plus 1. To find the parent, index, you simply use your own index divided by 2. So take a look of this one. To find the parent of node B, which is at index of 2, you divide it by 2, you get an index of 1. So you know that's where your parent's going to be. If you use 3 divided by 2, you still get a value of 1 because both of them are integers. So you don't even need to care about is even number or odd number, because after the integer division, they will find your parent's index. This actually gives you an even better structure than linked list implementation, because linked list implementation can only go from the root to the children. Remember that one node have a data part and 2 pointers. You can only point to your children, but you cannot point back to the parent. Of course, it is possible to write the linked list with 1 data part and 3 pointers. Not only you point to your children, but also point back to your parent. However, it's more complicated compared with this one-dimensional array implementation. Everything is actually very straightforward. Binary heap has 2 criteria. Let me repeat that one more time. The first criteria is that it has to be a complete binary tree. So it has a very fixed structure to give you the best performance you can ever achieve. In a binary heap, the second criteria is that for every node X with a parent P, the value that you store in P is smaller or equal to the key in X. So that it gives you, since it gives you an equal sign over here, it is possible that we can handle the duplications. If you take away the equal out of this definition, now that means that we will only be able to handle all the values without the duplications. So it depends on the need of the problem. But adding an equal sign is pretty straightforward. Binary heap is extremely simple. It only has 3 different functions that we need to worry about. The first 2 functions are the key functions. The build heap function is a function to help us build up a heap in a very fast way. So that all of these functions are very important in terms of to either construct a binary heap, use adding elements of the binary heap, or we can do the deletion of the binary heap. While one thing I want to mention before we go into the next topic, insert, delete, or build heap functions, you need to understand, if we are saying the second criteria of the binary heap is that the parent is always smaller or equal to all of its children, think about this. Where can we find the minimum value? Of course, the minimum value has to be the root. That's why we say in the very beginning, for priority queue, we can insert all elements that we want. However, we want to find the best way to retrieve the minimum value, and that is located at the top of the tree. And that is a very important concept you need to capture before we move into the functions. Now, let us take a look of the insert operation. For insert operation, is implemented by creating a hole at the next available location. Because think about this. If we currently have 10 elements, since it has to be a complete binary tree, the next element that we need to be inserted has to be the next available location. So what we are going to do is that we create that space and then put the value that we want to insert into that space, and then we try to satisfy the second criteria. Since we put next available location as the insert location, we satisfy the first criteria already. Now, as long as we're taking care of the second criteria, indicating that all the parents has to be smaller or equal to its children, as long as that is satisfied, then we have finished our insert operation. Very straightforward. Insert takes constant time on average, but log time in the worst case scenario. So let's take a look at this. Saying that this is our current binary heap, we have several items over here. Pay attention, 13, which is the root, is actually the smallest element compared with all of the values. 21 is smaller than all of its children. 16 is smaller than all of its children here. That is the only criteria about the value. And of course, the completeness of the binary heap is another criteria. And obviously, this is a complete binary tree. So now, say now we want to insert a value of 14, let us do this. That's creating a hole to satisfy the first criteria first. Assuming that 14 is in here. So we satisfy the first criteria now. Now we need to move into the second criteria to see if 14 is in its right spot. Compare with 31, which is 14's parent, we realize that no, it's not. So what we need to do is that this is what we call percolating it up to here. So 14 stays here, compare with its parent. And pay attention, remember this, whenever you try to find a parent, you simply divide your own index by 2. If they need to swap, they need to swap. So that is a while loop. If they find in the right space already, then you can stop the loop. So 14 compared with the value of 21, we need to percolating it up. Now 14 compared with the root, which is 13, you will find out it doesn't need to swap at all. And you can stop over there. That is the complete operation of the insert binary heap. Let's take a look at one more example and then saying that we want to build a heap from nothing. So in the beginning, you see that we will have an empty array with the capacity equals to 12, and we need to sacrifice the first location because index 0 is a problem, because when no matter index 0 going to multiply by 2 or multiply by 2 plus 1, they will not give you the property of left child or right child because 0 multiplied by 2 equal to 0. That's a special case here. Starting with an empty array, saying that we want to insert the very first element 15, then the binary heap would be 15 as the root. And that is the case that you need to put 15 into the index of 1. This gives you the same property. First of all, create the next available space, which is index of 1. Put 15 over there, try to find its parent. And basically, you see that this is going to be the process. Now, if we want to insert one more element, 30. 30 has to store in the next available location, so 30 will be an index of 2. And look into its parent to see is 30 less than the parent, which is not, so that we can simply put 30 over there. If we try to insert one more element, 18, it has to be in the next available location, so we will put 18 over here. Compare with the parent, finding 18 has no problem, so we can let 18 stays there. Now, if we try to insert one more item, which is 10, then we will put 10 into the next available location. Pay attention to this one. So now, 10 is in index of 4. It needs to compare with its parent, just like what we need to see over here. So index of 4 divided by 2 equals to index of 2. You need to compare with the element stays in index of 2, understanding that 10 is actually smaller than that. So you need to do the swap. And therefore, you will need to swap the two values, make 10 up over here, and then 30 goes down. In the next thing, you can see that we will need to swap the two. But that's not the end of it. So the index of 2 need to find the parent, which is the index of 1, continue doing the comparison, finding that they need to be swapped. And therefore, they need to be swapped and then generating the complete binary tree which satisfy the ordering property that makes it become a binary heap. So if we keep going, saying that I want to insert another value of 5, so 5 will be stored over here, and then you need to compare with its parent. So 5 divided by 2 equals to 2. So you need to compare with the parent, which gives you the index of 2, and that's the value of 15. So you need to swap the 2. So when the 2 have been swapped, they need to go over there. But it's not the end of it. You still need to compare with the root, which is the parent and index of 1. They need to be swapped so that you can see the binary heap is going to be looks like this. If we're going to insert the next value as 40, 40 will be put into the next spot, compare with the parent. 6 divided by 2 equal to 3. So you compare with the value of 18, realizing you don't need to be swapped at all. So that's the right place. Saying that I want to insert another value, which is 16. So the 16 will state an index of 7. Index of 7 divided by 2 equals to 3. So compare 16 with 18, realizing they need to be swapped. So they will swap the two values, swap over here, and it's again not the end of it. You still need to compare with the parent. So 3 divided by 2 get the value of 1. Then you will see 16 is not smaller than 5, so that is the right space, and we can stop over there. These are the approaches for us to do the insert operation. Very straightforward. Satisfy the first criteria first, and then worry about the second criteria.